Welcome to AI Paper Slop, the YouTube series where we take the fire hose of ML research and distill it down to the exact insights you need to build better systems. Today, we're diving into a paper from Microsoft Research and the University of Amsterdam called Multi-Turn On-Policy Distillation with Prefix Replay. So look, if you are training LLM agents right now, you know that on-policy distillation, or OPD, is just incredibly expensive. It requires live environment rollouts and teacher queries at every single step of your training loop. Today's paper introduces ReOPD, which completely removes the live environment by reusing offline teacher trajectories or prefixes that you already collected during RL training. By using this really clever step-decaying schedule to balance how relevant the data is to the student against how reliable the teacher's advice actually is, ReOPD trains at least 4 times faster, requires 0 tool calls during training, and actually preserves or even improves accuracy compared to standard online OPD.
Yeah, and it is a massive operational win for anyone working on multi-turn agents. But to really appreciate why removing that live environment is such a huge breakthrough, we need to quickly contextualize what engineers are currently suffering through with the baseline methods. So when you're training a model to execute a multi-step task,
Like, say, using a Python interpreter, reading the output, and then querying a search API.
exactly. The easiest starting point for that is supervised fine-tuning, or SFT. You just take a data set of perfect human-curated or teacher-generated trajectories, and you train the student to predict the next token.
Right, which is entirely off policy.
Precisely. And that introduces a pretty fatal flaw, which is known as exposure bias. Because the student only ever trains on the master path, it literally never sees what mistake looks like.
Yeah.
So during inference, the second the student hallucinates a slightly wrong Python command, it finds itself in a state space it has never encountered in its training data.
It just panics.
It panics.
Uh-huh.
It has no idea how to recover. It writes more bad code, the errors snowball, and the entire agentic loop fails. So SFT gives you a model that is great at acting perfectly, but just entirely incapable of course correcting.
Which is, the exact opposite of what you want an autonomous agent to do. So we know on-policy distillation fixes this exposure bias by forcing the student to generate its own paths and having the teacher correct it dynamically. But at what cost? Like, when we start talking about multi-turn agents, let's unpack the actual engineering reality of this.
Oh, the cost is staggering. I mean, both in compute and infrastructure. Let's just walk through the mechanics of traditional online OPD for an agentic task.
Yeah.
At every single turn, your student model proposes an action.
Right.
To find out what state that action leads to, you have to actually execute it in the live environment.
Yeah.
If your agent writes code, you need a sandbox Python execution node.
Yeah, and if it searches the web, you need a live web scraper or some API connection.
Exactly. And you have to keep all of those complex stateful environments alive and running during the entire training loop.
Which, if you are an ML engineer listening to this, you know is an absolute nightmare. I mean, we are talking about managing live Kubernetes pods, dealing with random network latency from external APIs, handling Docker container crashes.
All just to get the observation for your next training step.
Yes, it completely bottlenecks your gradient updates. You're just sitting there waiting on a Python script to fail.
You nailed the exact pain point.
Mm-hmm.
The environment execution latency is just brutal.
Yeah.
And it doesn't even stop there. Once the environment returns the observation, say you get a syntax error message from Python, you then have to query your massive teacher model to provide the ideal target distribution for that specific newly generated history.
Oh, right.
So now you are constantly pausing your training loop to run fresh inference on a 70 billion parameter teacher model over and over again on entirely new data at every single step of the multi-turn interaction.
It's just wild. Think about learning to fly a plane, right? SFT is just sitting in a classroom watching a master pilot's perfect flight recording. It's incredibly safe, but if you hit unexpected turbulence in the real world, you have no idea what to do because you've never felt the plane shake.
Right.
Standard online OPD is like forcing the master pilot to sit in the co-pilot seat of a real plane while the student just randomly yanks the controls. The student throws the plane into a nosedive, and the master pilot has to instantly calculate the optimal way to recover from that specific nosedive. It is highly effective for learning, but it is dangerous, slow, and incredibly expensive to operate.
That's a great way to put it. And let's push that analogy even further. Imagine that student isn't just learning to fly one plane.
Okay.
They're learning to fly a helicopter, drive a submarine, and operate a drone all at once.
Mm-hmm.
If you want to train a generalist agent that handles mathematical reasoning, web searching, and terminal execution, standard OPD requires you to deploy and maintain all of those heterogeneous environments simultaneously during the training loop.
Yeah, the operational complexity doesn't just scale, it multiplies with every new environment you add.
Exactly.
Which is exactly why most teams look at online OPD, look at their compute budget, and just, stick to SFT while crossing their fingers.
Right, they just hope for the best.
So this brings us to the core of the paper. How does ReOPD get the benefits of the live copilot without actually having to fly the real plane in a live environment?
Well, the secret is offline prefix replay. ReOPD completely ditches the live environment by relying on a fixed pool of offline teacher trajectories. And the brilliant part here, at least from an engineering perspective, is that this data is essentially free.
Free data is the best kind of data. How is it free, though?
So if you are training your teacher model using a reinforcement learning algorithm like GRPO, which is the industry standard right now for reasoning models, you are already generating thousands upon thousands of on-policy rollouts from the teacher during its own RL phase.
Oh, of course. You just save them.
Exactly. ReOPD just takes those saved historical trajectories. During the distillation phase for the student, instead of spinning up a live Python sandbox, ReOPD just replays the teacher's prefix. It feeds the student all the previous actions and environment observations up to a specific step, let's call it step T, straight from that offline data.
Wait, hold on. Let's unpack this carefully, because I feel like we were walking into a trap here.
Okay.
If the student is just acting on top of a completely teacher-forced prefix like a history of actions that the teacher took, aren't we just back to square one? How is this actually on policy if the student didn't naturally navigate to that state itself? It feels like we are just feeding it the master pilot's perfect flight recording again, which is exactly the SFT exposure bias problem we were just trying to avoid.
Your intuition is spot on, and you've basically just identified the core theoretical contribution of this paper. Researchers literally call this the prefix trap.
The prefix trap. Okay.
Yeah. When you move from live online interaction to static offline replay, you introduce a highly complex two-sided distribution shift. The math here is really elegant because they actually bound the gap between the ideal interactive objective and this offline objective, and it decomposes perfectly into two competing forces.
Okay, two competing forces. Let's take them one at a time so we don't get lost in the math. What is the first side of this shift?
The first side is what they call the student occupancy shift, and this maps exactly to your concern. The teacher's recorded prefix, the sequence of states it visited, is not the sequence of states the student would naturally visit.
Right. The teacher might write a highly efficient list comprehension in Python, while the student would naturally write, like, a clunky for loop.
Exactly. So if we just blindly train the student on the teacher's prefixes, we lose relevance to the student's actual test time behavior. The student occupancy shift basically measures how far the offline data diverges from where the student actually needs practice.
Makes total sense. If we want the student to learn how to recover from its own unique mistakes, the prefix needs to look like something the student would actually do. So the obvious solution seems to be, well, why don't we just let the student generate the whole prefix offline and then ask the teacher to greet it later?
Because the moment you do that, you trigger the second side of the trap, which is the teacher reliability shift.
And what happens there? The teacher just gets confused.
Basically, yeah. We have to remember that the teacher isn't an omniscient God, right? It's an LLM too. It has its own manifold of reliable support, like the types of code and logic it actually understands well.
Right.
If you let the student go completely off script and generate a weird, highly suboptimal hallucinated history, and then you query the teacher for a target distribution on that exact state, the teacher's advice often becomes complete garbage.
Because you've dropped the teacher into a deeply hallucinated, broken Python state that it would never naturally reach itself.
Correct. The teacher hasn't been trained to operate in that bizarre corner of the state space. Its conditional probability distribution becomes highly unreliable. It starts hallucinating too. So if you make the prefix more student on policy to fix the first shift, you destroy the reliability of the teacher's supervision, which is the second shift.
Wow. That is a massive catch-22.
It really is.
You absolutely need the state to be relevant to the student so it learns to recover. But if it's too relevant to the student's natural flailing, the teacher goes out of distribution and gives terrible advice. So how does ReOPD possibly balance student relevance with teacher reliability when all they have is a static data set of teacher rollouts?
This is where ReOPD transitions from a theoretical bound to just a brilliantly simple engineering implementation. They frame multi-turn distillation as a reliability-aware prefix distribution problem. They basically need to find an effective history distribution that sits right in the Goldilocks zone, between the student's occupancy and the teacher's reliable support.
Okay.
And to achieve this, they introduce a step-decaying weight parameter called kappa.
Kappa. Here's where it gets really interesting. How does a single parameter bridge that massive distribution gap?
It leverages the dimension of time, specifically the step depth within a trajectory. So think about the very early steps of an agent's task. At step 1 or step 2, the student and the teacher are highly likely to agree. The distribution shift is incredibly low.
Right, because they haven't had time to diverge yet.
Exactly. Because of that, the teacher's early prefix is actually a fantastic surrogate for the student's natural path.
Yeah, they're both looking at the exact same initial prompt. The board is clean.
But as you move deeper into the trajectory, say step 10 or step 15, the compounding differences multiply. By late steps, the replayed teacher prefix is a terrible surrogate for the student. The student occupancy shift is huge.
Yeah.
If we force the student onto that deep, complex teacher path, we are training it on a state where it will never actually have the capability to reach on its own. Conversely, if we somehow forced a late student path into the mix, the teacher reliability would completely crater.
Let me make sure I'm visualizing this correctly. It's like getting walking directions in a massive foreign city. At step 1, leaving the hotel lobby, the concierge's advice is 100% reliable. The path is obvious. You and the concierge are in exactly the same starting state.
Right.
But by step 15, if you took 3 wrong turns down some random alleyways, the concierge's pre-written instructions about turning left at the bakery are completely detached from your current reality. If you try to apply them, you're just going to get more lost.
I love that framing. And to connect that analogy back to the math in the paper, how do we measure exactly how far down that random alleyway you've wandered compared to the concierge's original map?
Right.
The paper defines this theoretically by looking at the accumulated student-to-teacher likelihood ratio over the prefix. They essentially want to measure the probability of the student taking that path versus the probability of the teacher taking it.
But wait, calculating that exact likelihood ratio per history across an entire dataset sounds incredibly computationally expensive. You'd have to run full inference for both models over every single token of the history just to get the weight.
You're absolutely right. The variance would be huge, and the compute cost would completely ruin the efficiency gains they're going for. So instead of calculating the true likelihood ratio, they implement a surrogate. It's a normalized position index sampling schedule driven entirely by that parameter kappa.
So they just use the step index, the literal turn number in the conversation, as a proxy for how bad the distribution shift is.
That's the elegant shortcut. They set kappa to a value less than 1. In their main experiments, they found kappa around 0.6 works beautifully. The sampling weight for any given step TED is simply kappa to the power of t.
Okay, let's do some napkin math on that for a second. If kappa is 0.6, step 1 gets heavily sampled. But by step 5, you are doing 0.6 to the 5th power, which drops the weight down to, what, about 7.7%?
Yeah, right around there.
And by step 10, the sampling weight is well under 1%.
Exactly that. It is an aggressive exponential decay. By doing this, they are effectively amputating those late-stage hallucination zones from the training distribution. They are acknowledging that they have to use offline teacher prefixes, but they focus the vast majority of the distillation updates on the early steps, where those prefixes are actually relevant to both the student and the teacher.
It really is a brilliant workaround. You completely avoid the live Kubernetes pods and API latencies by using offline data, and you avoid the exposure bias trap by aggressively decaying the weight of the deep, irrelevant steps. But at the end of the day, theory is just theory, right?
Always.
What does this all mean for actual performance? Does aggressively cutting out late steps actually translate to benchmark dominance on state-of-the-art models?
It absolutely translates, and the benchmark results reveal some really fascinating dynamics about how LLMs handle different types of state spaces. They tested ReOPD using the Qwen3 family of models, specifically distilling into a Qwen3 4B student from much larger 8B and 30B teachers. And they evaluated this across 2 very different types of environments. First, math environments, using a Python tool on rigorous benchmarks like AIM and Math 500. And second, search environments, evaluating on a Hotpot QA and Trivia QA.
I have to imagine math and search stress the agent in completely different ways. Like, a wrong move in Python is very different from a wrong move in a web search.
They do, and that fundamental difference defines the 2 distinct performance regimes outlined in the paper. Let's look at the math environment first. Here, the capability gap between a 4B student and a 30B teacher is massive. Math requires long, precise chains of logic and exact syntax.
Right.
If you use standard online OPD for complex math,
Yeah.
the 4B student quickly proposes a flawed Python action, maybe a syntax error or a logical dead end. The state drifts far from the optimal path, and the teacher is suddenly forced to grade a deeply suboptimal, confusing Python state. The teacher's reliability just breaks down entirely.
Going back to our analogy, it's because the master pilot has never seen a plane fly upside down through a canyon, so their advice on how to pull out of it is actually worse than useless. The teacher just starts guessing.
That is the core issue.
Yeah.
And because of this dynamic, in the math environment, ReOPD actually beats standard online OPD.
Wait, it beats it?
This is the craziest part of the paper.
Yes.
Yes. For example, when distilling a Quen 3AB teacher into a Quen 3-4B student on these math tasks, standard online OPD achieved a 55.1 average on the benchmarks. ReOPD, using just the offline prefixes with the kappa step decay, boosted that to 57.2.
55.1 up to 57.2. That is wild. It's not just operationally faster because you drop the live environment. It's actively better for the model because it protects the teacher from its own out-of-distribution incompetence. It anchors the student to the reliable early parts of the teacher's logic and shields everyone from those chaotic late-stage hallucination states.
Exactly.
But what happens in the search environment? Does the same logic hold there?
In search, the dynamic flips because the nature of the environment is much more forgiving. The capability gap between a 4B and 30B model for basic retrieval tasks is much narrower.
Okay, yeah.
If the student pulls a slightly different Wikipedia paragraph than the teacher would have, it doesn't fundamentally break the state space the way a syntax error in Python does. The context window just has different text in it. Because the state isn't broken, the teacher remains reliable even on student-induced histories.
Ah, so the teacher reliability shift isn't as severe in search.
Right. And in this regime where the teacher's advice stays good deeper into the trajectory, ReOPD perfectly matches the performance of online OPD. Doesn't beat it by 2 points like in math, but gets the exact same state-of-the-art accuracy without ever having to spin up a live search API during training.
Which brings me to a really counterintuitive finding I noticed deep in the paper. We've been talking about using these offline prefixes to train our 4B student. If we want the absolute best, most flawless prefixes to serve as the guiding track for our student, shouldn't we use an incredibly massive, ultra-smart model, like a 32B or 70B model, to generate the offline prefix pool? Better, smarter data should mean better distillation, right?
You would certainly think so. I mean, that's the prevailing logic in most SFT pipelines today. Always use the biggest model available to generate your data. But the paper proves otherwise for on-policy distillation. They ran a fascinating prefix source experiment. They fixed the teacher model, the one actually providing the gradient updates, as the Quen 3-8B model.
Yeah.
But they varied who actually generated the offline prefix pool.
Okay.
They tried prefixes generated by a 4B, an 8B, and a 32B model.
And let me guess, the 32B prefixes didn't win.
The best performance came when the prefixes were generated by the 8B model, the exact same model acting as a teacher.
Let's take that a step further, because that really feels backwards. A 32B model's highly advanced prefix makes the 8B teacher worse at its job. How does that mechanism even work?
It is the ultimate validation of the teacher reliability shift theory we discussed earlier. If a 32B model generates a brilliant, highly complex prefix, maybe uses an advanced, obscure Python library or a highly sophisticated multi-hop search strategy, the 8B teacher has likely never seen that specific strategy.
Right.
Would never naturally reach that state on its own. So when you ask the 8B teacher to provide the conditional probability for the next action on top of that 32B prefix, the 8B teacher is suddenly out of distribution. Its advice becomes unreliable because the context is quite literally too smart for it.
That is a fundamental paradigm shift for how ML engineers need to think about dataset generation for agents. It's not about finding the objectively best or smartest trajectory in a vacuum. It's about finding the trajectory that your specific teacher model actually understands well enough to grade reliably. If the teacher didn't walk the path, it can't tell the student how to take the next step.
Precisely. The distillation target relies entirely on the alignment between the prefix and the teacher's internal representations. And, there's one final massive operational detail that makes ReOPD such a win for anyone managing an ML cluster. Because ReOPD is totally decoupled from the live environment, you can seamlessly merge your offline datasets.
What do you mean by merge?
Well, If you're building a generalist agent, you no longer need a brittle training loop that simultaneously calls a Python execution node for one batch and a live web browser for the next batch.
Oh, wow. Yeah.
You just take your offline math GRPO data and your offline search GRPO data, merge them into one unified static pipeline, and train a single joint student. The researchers show they could train a single 4B student jointly on both domains simultaneously, and it stayed perfectly on par with standard OPD, with absolutely zero live tool calls during distillation.
That is absolute music to the ears of infrastructure teams everywhere. So, to synthesize this whole exploration of the paper for our listeners, ReOPD takes the historically expensive, environment-heavy, latency-ridden process of agent distillation and turns it into a fast, reusable offline resource. By acknowledging the strict limits of teacher reliability and heavily sampling the early steps of a trajectory via a kappa step-decay schedule, it elegantly sidesteps the prefix trap. It achieves 4x faster training, requires zero tool calls, and preserves, or in the case of complex math, actually improves the rich density of on-policy learning. If you are engineering ML agents, you don't need to suffer through complex live environment loops anymore. Just reuse your GRPO rollouts, apply this step decay weighting, and you have state-of-the-art distillation.
It really redefines the infrastructure requirements for agentic AI, making it dramatically more accessible.
Sure.
But if we connect this to the broader trajectory of AI development, it leaves us with an important lingering question. ReOPD proves definitively that a teacher can only reliably supervise a student along its own familiar paths. The kappa step decay schedule explicitly anchors the student to the teacher's reliable support zone. But if we lock our students entirely into the teacher's comfort zone just to ensure reliable gradients, how will we ever distill agents that can dynamically discover completely novel tool use strategies that neither the student or the teacher has ever seen before?
The ultimate tension between safe imitation and true, boundless exploration. If the student never wanders down the dark alleyway, it never discovers the shortcut. That is definitely something for you to ponder the next time you kick off a massive training run. That's it for today's video on AI Paper Slop. Keep pushing the boundaries of what these systems can do, and we'll see you on the next deep dive.